Hello guys, all of you can hear me properly. I'm audible to all of you. Perfect. Just note down the syllabus part. So under structural dynamics, we have this syllabus free and forced vibrations. Structural dynamics, when you focus free and forced vibration, we do have free and forced for undamped and damped vibrations, damped and damped vibrations, single degrees of freedom. Then we have a free vibration of a undamped at 2 degrees of freedom. I'm going to cover the single degrees of freedom. 2 degrees of freedom will be covered by Dinesh, sir, right? Under these vibrations, like a free and in the particularly free vibrations, like if you categorize the vibration, we have the two types generally. One is a free vibration, other is a forced vibrations. Under free vibration, we have undamped free vibration, damped free vibrations. Under forced vibration, we have undamped forced vibrations, damped forced vibrations, right? If you talk about the weightage we have around 6 to 7 marks, including 2 degrees of freedom, right? Under single degrees of freedom, what are the topics that we need to cover? First of all, the basics. Then free undamped vibration we need to cover. Free damped vibration we need to cover. Forced damped undamped vibrations, magnification factor, and transmissibility. These are the topics, my dear friend, that we need to cover, right? What are all the books that we need to follow? SS Rao for concept and numerical, GK Groover, again VP Singh. My suggestion would be you follow only SS Rao. That will be sufficient enough, right? Then guys, all of you have noted down the syllabus part and what are all the topics that we need to cover. Is it done for all? Perfect. Not only fundamental of vibrations. Now, when you talk about the fundamental of vibration, it's a very simple. To explain the fundamental of vibrations, let me give you the example of pendulum. Everybody must be aware of this particular pendulum. For example, we have the ball which is being attached to the string. The total system we are calling it pendulum. This rod or string is having a length, for example, L. By default, if I disturb the system, let me just show here. The length is basically what L. If I disturb the system, for example, this is the equilibrium positions. What is the meaning of equilibrium positions? We also call mean position. We also call zero positions. We also call zero position. Understand? Equilibrium position, mean position, or zero position that we call the position where exactly the net force and the net torque will be zero in the system. You can see at this position, my friend, on the ball, there is a weight mg and there's a tension in the string is T. and that will be balanced out, no doubt about it. What happened when I disturb my system from its equilibrium position to this position? Something like this. If I disturb my system from this position to this particular position, that means this ball and the string is getting tilted by the angle theta. That is the disturbing torque which we have applied. Then what will happen, guys? Whether system will come back to its original equilibrium position or not. For example, this is mg. Mg got two components. One is what, guys? This angle will be theta. This will be mg cos theta. This will be mg sin theta. Now you only tell me this mg sin theta and L that will create some restoring torque or what? Check it out. Tell me guys, mg sin theta will create some restoring torque or not? About point 0, for example. You can see this. Mg cos theta will pass through the center O, so it will not create any torque. But mg sin theta into L, mg sin theta into L, that will create my different what? Restoring torque, restoring moment. And that will bring the system from its what? From the disturbed position to what? Equilibrium position. But my friend, while returning to this, while doing the journey from point B to point A, the ball will not stop at the point A. It will again come, it will go back to the what? This position. Why? Because of the inertia. Because of the inertia. And again, from here we got the mg, it got two component. And because of the mg sin theta, again it will come back to its what? This equilibrium positions. And in doing so, it will try to oscillate about this mean position to and fro. So what we are understanding, the fundamental of vibration is that the body is said to vibrate if it is doing to and fro periodic motion. We will understand what is the meaning of periodic motions, what is the meaning of periodic functions, what is the meaning of to and fro motions. As of now, you please note down. You can note on the example also. Example, a swinging of a pendulum on either side of the mean position takes place under the action of a gravity. Here, restoring, what is the restoring element? Gravity. When the pendulum swings through the mid position, its center of mass is at the lowest position and it possesses only the kinetic energy. But at the each extremity of the swing, it has only potential energy because it is getting some height and the kinetic energy will be zero. But the moment it is getting back to its equilibrium position, it is getting somewhat kinetic energy. In the absence of any friction, the motion will continue infinitely. That means whatever the ball is there attached with this string, it will keep on oscillating about its mean position like this. That will continuously happen. And that is called as oscillation or vibrations in the system. All of you have noted down. Can I move to the next one? Note down the types of vibrations. We have the different types of vibration, guys. Free vibrations, that is called natural vibrations. The free vibration basically happening because of the initial disturbances. There is no time varying force present in the system, but we have disturbed the system, and because of the inertia, it is trying to doing the oscillations. Elastic vibration in which there is no friction, an external force, basically there is no friction, there is no external force after the initial release of the body. That system will be called as free or natural vibrations. That means I told you, right? There is a ball, pendulum, you disturb it, it will be getting what some height, and once you release it, it will be coming back and it will be going like this. And continuously it is oscillating about its mean positions. That means initially whatever the disturbing torque we have applied, that will be gone. That will be zero after some point of time. Once you disturb it, it will be gone. Once you disturb the system, that disturbing element will be gone. Now it will be continuously oscillating because of its own gravity. That type of vibration will be called as free or natural vibrations. Damped vibration, same thing, but extra thing is there, that is nothing but damper. Damper will also be present in the system like this. Now there is a damper in the system. When there is a damper in the system, my friend, what will happen, guys? Whatever the oscillation that was continuously happening, that was continuously happening with the same magnitude, but now because of the damper is nothing but friction, fluid friction. And because of the fluid friction, that oscillation will be die out after some point of time like this. Exponentially, this particular oscillation will be die out. Those type of vibration will be called as damped vibrations. When the energy of the vibrating system is gradually dissipated by the friction and other resistance, this vibration is said to be called damped vibrations. Right. Third is a forced vibrations. Like when there is a repetitive force continuously act on the system, then the vibration are said to be called as forced vibrations. Right. And the frequency of the vibration is that of the applied force, and it is independent of their own natural frequency of the system. In the damped vibration, basically we have the three types of damping. In the particularly damped vibration, we have the three types of damping. One is a viscous damping, column damping, hysteresis damping. Hysteresis damping is also called structural damping. Structural damping. Not only symbolic representations. For a viscous damping, that is called as fluid friction. Column damping, that is called solid friction. Hysteresis damping means what? Intermolecular friction damping. Right? Let's suppose we have a spring mass system. Suppose we have a spring mass system. There is a spring and there is a what? Suppose we have this hysteresis damping. That is what the representation is. If I disturb the system from its equilibrium positions, it will oscillate, but that oscillation will be die out after some point of time. You know that when the body is moving and if there is a huge amount of friction, that body motion will stop after some point of time. If there is no friction in the system, that motion will be continuously happening. Infinitely it will happen. That is what happening in the free or natural vibrations. We also got undamped free vibrations. But when you talk about the damped vibration, we have the three types. No, no. Periodic motions. What do you mean by the periodic motions? A motion which repeats after equal amount of time or equal interval of time, that is called as periodic motion. A best example is simple harmonic motions. To explain further what is the meaning of periodic motion, let me explain you. Suppose we got the equation of a motion. You will come to know what is the meaning of equation of a motion. But as of now, you consider like a situation we have a displacement versus time graph, something like this. And that graph is varying sinusoidal way. X is equal to x naught sine omega n t. My dear friend, sine, whatever the sine function is there, that is a periodic function. And everybody know what is the period of sine? It's a 2 pi. It's a 2 pi. After every 360 degree, that function will repeat itself. That particular curve will repeat itself. So what is happening? It is not only periodic function, but it is doing to and fro motion about its zero position. You can see that it is going above, it is going down, going above, going down. That type of system is said to be called as what? The vibration will be exist in that particular system. That is example number A. What is the example number B? Suppose if I represent like x is equal to x naught sine square omega n t. Now, sine square omega n t, it's a periodic function, but it is not doing any kind of oscillation to and fro motions about the mean position. It is only doing one motion. See that? Only one-sided motion is there. One-sided motion. That type of system, we say that there is no vibration is being exist. It's a periodic motion, but there is no vibration because it is not doing to and fro motion. So, very first criteria to have a vibration is that it should be periodic. Second, it has to be to and fro. Both the condition need to be satisfied. Third, my different example, I'm giving you some exponential function. Again, exponential function is not only periodic function, it's neither a periodic function nor a doing any to and fro motions. So again, there is no vibrations. Again, there is a no vibrations. Then, no, 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 one more term, time period. What is the meaning of time period, guys? This is the first term. Second is a time period. The time to taken for our system to complete one particular cycle, that is called as time period. Yes or no? Yes or no, guys? Time taken for a system to complete one particular cycle will be called as time period. Yes or no, guys? Note down frequency. Note down the frequency. How how many number of cycle is being completed per unit time? That is called as frequency. And what is the relationship between frequency and angular speed? It's a 2 pi nu. Sometimes we write omega is equal to 2 pi nu. Sometimes we write by the representation of f, frequency f, small f. What is the meaning of amplitude? The maximum displacement of a vibrating body from the mean position, that is called as amplitude. That is called as amplitude. Then what we can do, we can just note down degrees of freedom. Next topic, degrees of freedom. The number of independent coordinates are required. The number of independent coordinates are required to specify the complete motion of a system. Or you can also say how many displacement variables are required to specify the position of a mass or a system. That is called as degrees of freedom. How to find the degrees of freedom for any system? It's a very simple. Always give some displacement variable to the mass. Whatever the mass is whatever the mass in the system. Let's say two mass, give two displacement variable. And let's check it out whether those displacement variables are dependent or independent. Let's say, for example, number one, we have a spring mass system in a vertical positions. The mass is getting displaced by the amount x, for example. Now, how many displacement variables are there? One. So how many degrees of freedom? One. How many natural frequency? One. Getting my point? All of you understanding what we are talking about? If you come back to the question number two, you can see that in the question number two, we have basically two masses. You can see that there is a two masses, and those are connected with a different spring stiffness K1 and K2. Now, I told you if you want to find the degrees of freedom, we need to give the displacement variable to each and every mass. I have given the displacement variable x1 and x2 to each and every mass, m1, m2, and I'm checking whether they are dependent or not. And I found that when the mass m2 is displaced by the amount x2, definitely mass m1 will not be displaced by the same amount because there is a stiffness k2, and the k2 stiffness and k1 stiffness is different. They are not same. So definitely x1 will not be equal to x2. There's a sure sort guarantees there because there is a flexible link in between that. In between there is a flexible link. This is a flexible link, right? We call flexible link, not a rigid link. So degrees of freedom is how much? How many degrees of freedom will be? Two. Then how many natural frequency? Two. Omega n1, omega n2. Come back to the example number three. In example number three, you can see that there is again same example, but now that flexible link, spring number two, is getting replaced by rigid link or rod. Everybody know rigid link or rod is non-deformable member. That means mass m2 will be displaced by the amount x2. Mass m1 has to be displaced by the same amount x1. There is no other option. So now we have the two displacement variable, but those two displacement variable will be what? Same. X1 equal to x2. So how many degrees of freedom? One. How many natural frequency? One. If you want to convert this system into equivalent system, we can represent like this. Like this. No doubt. Very, very important. Done? Is it done, guys? No, no, quickly. No doubt. Example number four. Now we are discussing the continuous system. Example is cantilever beam, a flexible cantilever beam which is having certain weight. Now, my dear friend, you can see that suppose if I disturb this rod, if I apply the moment, disturbing moment, you can see that this mass of the rod, this particular mass which is having certain mass, this rod is having certain mass. This particular rod will consist of so many masses. I can think like infinite mass. To each and every mass, if I allot this displacement variable x1, x2, and x3, x4, x5, x6, this displacement variable will not be equal. Will not be equal. There is no other options. They will not be equal. Why they will not be equal? Because whatever the deflection is there, that is what we have a bending deflections. So definitely they will not be equal. It's a cantilever beam. They will not be equal. So how many degrees of freedoms are there? If there is an infinite mass, infinite displacement variables are there. If there is an infinite displacement variables are there, infinite degrees of freedom, infinite natural frequencies. If we talk about the example number 5, rod which is having a certain weight, rod which is having a certain weight, again we are having so many masses. A rod can consist of so many infinite masses, right? To each and every mass, I allotted x1, x2, x3. But each and every displacement variable can be replaced, can be correlated to the what single displacement variable like theta. Because x1 is what? A into theta. X2 is what? B into theta. X3 is what? B plus C into theta. So they are dependent. They are depending on each other's. They are depending on each other. So how many displacement variables are required? Only one theta. That's it. If you just specify theta like a 30 degree, 20 degree, 1 degree, 2 degree, that will be sufficient enough to talk about the position of a system. Then how many degrees of freedom? One. How many natural frequency? One. Right? No doubt. No, no, no. Example number 6. Example number 6. If you see, we have the rigid cantilever beam. My different when we have a cantilever beam, that too rigid one. Tell me guys, any kind of deformation will be there? If there is a no deformation, any displacement variables will be required to specify the system. Confirm it. If there is a rigid cantilever beam, that means it cannot be deflected, then any displacement variable will be required to each and every mass. Suppose infinite masses are there. Do we require any uh, like a variable to specify the positions? No. So what are the degrees of freedom? Zero. Zero. Example number 7. There is a spring and there is a pendulum which is being attached to the mass. Now here might define how many displacement variables are required. First, whatever the m dash is there, pendulum bob, whatever the bob is there, to this we require theta, and to the mass we require x. So how many variables? X and theta. How many degrees of freedom? Two. How many natural frequency? Two. Omega and omega and two. Omega and one and omega and two. If we talk about the example number 8, suppose we have a ball which is being connected to the two different strings. Two different ball, two different strings. One string is being tilted with angle theta 1. Second string is being tilted with angle theta 2. And both are not dependent. Both are independent. So how many degrees of freedom? 2. But if we attach these same two balls to the same spring, to the same string, there is a single string. Then my friend, what are the total displacement variables? Only theta. That's it. So what are the total degrees of freedom? 1. Already I mentioned the rod. So yeah. No doubt. Now we will start the types of free vibrations and we will solve some numerical based on that. Done everyone? No, no doubt. No doubt, my dear friend. It's a very, very important. The types of free vibrations. The types of free vibrations. First is a longitudinal vibrations. Second is a transverse vibration. Third is a torsional vibrations. Third is a torsional vibrations. When the vibrations are happening along the when the vibrations are happening or whatever the motions of the mass or oscillation of the mass is happening parallel to the axis of the shaft, those type of vibration will be called as longitudinal free vibrations. When the particle of the shaft or disk moves parallel to the axis of the shaft, then the vibration is known as longitudinal vibrations. In this case, shaft will be getting elongated or shortened alternatively. Thus, there is a what? Tensile and compressive stresses will be induced in the particularly what? Shaft alternatively. Understand what they're talking about. To explain this particular fundamental concept, I am giving one example of strength of material. Everybody know when the rod is being attached with the mass, the moment if I attach the mass, there is some static deflections. And everybody know how to find the static deflection from the static equation, from the strength of material equations, PL divided by AE. Yes or no? Yes or no, guys? Whether this particular equation is clear or not from the strength of material. Confirm it, please. Now, we can also replace W divided by K equivalent, where K equivalent is what? A by L, A by L, A by L. That is the elastic stiffness of this particular massless bar. And I can represent this into the equivalent spring mass system, something like this. And that stiffness I'm calling what? Longitudinal stiffness. Longitudinal stiffness. We will come to know what is the natural frequency. That formula is K by M. But here I'm writing K equivalent by M equivalent, where K equivalent is what? A by LM. What I want to say, the moment if I attach the mass to this particular massless bar, there is some static deflections. There is some static deflections. After that static deflection, my dear friend, I'm disturbing this mass. For example, the moment if I attach the mass is here, and there is a certain amount of static deflection will be there. From that static deflection, from this particular is basically equilibrium position, I'm disturbing this mass by the amount x. From this particular position, what I'm doing, I'm disturbing it from what, guys? I'm disturbing it what? I think, yeah. So this is nothing but static deflection they have given till here. That is a static deflection. From this equilibrium position, what I'm doing, I'm disturbing it by the amount x. If I disturb it, there is a further some restoring force will be developed in the form of what? Elastic. There is a certain amount of restoring force will be developed, my dear friend. That is called as elastic force. That is called as elastic force, right? Make a note of it. And at the equilibrium position, I told you, mg is equal to k equivalent into delta static. Whatever the initial spring force will be there. What is the initial spring force? K into k equivalent of spring into delta static. And that will be balanced out mg weight. So from there, what is the k equivalent by m? That is equal to g by delta static. So omega n can also be written as g by delta static. Now all of you have noted down. If you don't want to write this thing, you can just make a note of it from here to here. That will be sufficient enough. And you can just note on the example figure. No need to write each and everything of omega and how we are getting. Anyway, we will discuss separately in through numericals. Done? How about if I note down the transverse vibrations when the particle of the shaft or disc moves approximately perpendicular to the axis of the shaft, perpendicular to the axis of the shaft, then the vibrations are known as transverse vibrations. Transverse vibration. In this case, the shaft is straight and the bend alternatively, and thus the bending stress will be induced in the shaft. A very simple example: a cantilever beam subjected to the mass. When I attach the mass, the moment if I attach this mass, there is a certain amount of static deflection, and everybody studied that. Yes or no? In the strength of material, a cantilever beam subjected to end force P, everybody knows what is the static deflection formula: WLQ divided by 3EI. And if I want to write the in terms of W by K, then what is the K of bending? What is the bending stiffness? E 3EI by L cube. 3EI by L cube. If I want to represent this system into equivalent spring mass system, then I can write this might different K bending mass, and there is a static deflection. The moment if I attach this mass, there is a certain amount of static deflection that you can see very clearly through this figure. After this static deflection, I'm after this static deflection, my different what we are doing, we are disturbing the system by the amount x. From this equilibrium position only, we are disturbing this mass from this particular attaining after attaining this part. See, all the time there is a confusion in the basically many of the textbook. They treat like this system as a this position as a equilibrium position, but that is not a equilibrium positions. Always remember when I attach this mass, there is a certain amount of static deflection. And from the static deflection only, the moment it is deflected by the static deflections, after getting deflected, then only it is attaining the what? Equilibrium positions. From that equilibrium position, we need to disturb it. Then only the vibration can be there. Right? You need to understand the fundamental of static deflection. We will come to know through the numerical also. If you are having doubt, I have mentioned here the formula regarding the strength of material. If somebody will be asking you what is the natural frequency of the system, it's a very simple. K equivalent by M. But how we are getting K equivalent by M, that we will come to know through one example number one, question number one. Now, what is the meaning of transverse vibration? When the particle of the shaft is doing motion in a perpendicular, see that this is a mass which is oscillating like this, which is a perpendicular to the axis of the shaft. That type of vibration will be called as transverse vibration. Those type of vibration will be called as transverse vibrations. Note down torsional vibrations. When the particle of the shaft or disc is moving in a circle about the axis of the shaft, then the vibrations are known as torsional vibrations. Torsional vibrations. In this case, the shaft is twisted, untwisted alternatively, and the torsional shear stresses will be induced in the particular shaft. Let's say we have a rod and the disc is being attached, and the rod is what? This particular beam is a massless beam, right? If I disturb this disc by the amount of disturbing torque, then there is a resisting torque will be developed. And what is the resisting torque? Kt into theta. You might have studied in the torsional chapter. Torsional chapter. Angle of twist is what? Theta. That is nothing but TL divided by Gj. So what is the T by theta? That is called Kt or beta. That is nothing but torsional stiffness. Everybody know that. Newton meter per radian. That is a unit of Kt. Kt or beta, that can also be written as Gj by L. Gj by L. No, no, guys. The question number one, example number one, regarding undamped free vibrations of a single degrees of freedom. See, there are so many figures you can see, but note down this figure. Which figure? This figure. As a question. What is the question? If I disturb this mass from its equilibrium positions by the amount x, what is the natural frequency of the system? That we need to find it out. Note down. What is the natural frequency of the system? Note down each and everything, then I will explain. Understand, guys, there was a spring which is being basically what attached with the top particular, any hinge surface, or maybe it is just hang it from a particular, positions, in a vertical positions. And that is nothing but free length. The moment if I attach the mass to the spring, everybody believe that or not, there is a static deflections. From position number one to position number two, can you believe that there is a static deflections? Can you imagine? Rather than believing, can you imagine? The moment you attach this mass to the spring, whether there is a static deflection or not. Tell me, guys. There is a static deflection. The moment there is a static deflection, after attaining the equilibrium positions from the static deflection, after getting deflected by the statically, then we are disturbing it by the amount of x, by the disturbing force Fd. And that disturbing force will be run away after some point of time. It is gone. It will not be present in the system. That's why we are calling free from force vibration, free vibration or natural vibrations, right? If I want to draw the free body diagram at the mean position, what is the meaning of mean position? Equilibrium position, zero position. It is that position of a system where that position of a system where the net force and the net torque is zero. In this particular system, net torque is automatically zero. What about the net force? The net force has to be zero at the equilibrium position. What are all the forces are acting by different? Mg, that is acting in the downward. K into delta static, that is a spring force initially that is being developed in the spring, that will be acting opposite to the direction of a motion. And that mg will be equal to what? K delta static. Mg is equal to what? K delta static. Mg is equal to what? K delta static. That is our equation number one. That is our equation number one. After getting displaced, the mass is here. At this position, my friend, at this position, what I need to do? I need to draw the free body diagram once again. If I draw the free body diagram, there is a mg weight which is acting in the downward directions, spring force Now my different spring force will be how much total spring force? K delta static, which was originally present, but now there is an additional spring force will be acting in a spring, and that is nothing but K into X. K into X. So if you try to write down, now it is under motion. If you try to write down the Newton's second law, if you try to note down the Newton's second law, the net force in the direction of a motion, that is equal to ma. Ma. And what is the acceleration? Everybody know? dv by dt. What is the v? X dot. Then what is the a? X double dot. We can also write d square x by dt square. But here we will represent with the what? Always we represent with the what? X double dot. We don't write all the time d square x divided by dt square. We represent it x double dot. No doubt. Equation number one. We will utilize the equation number one. No need to worry at all. Now, my friend, the disturbing direction is what in this direction. If you write down the net force, if you write down the net force in the direction of a motion, mg acting in the downward direction, that is a plus. But k is static into x, they are acting in the what upward direction. So k delta static plus x, that is about the what minus sign. That is equal to mx double dot. That is equal to mx double dot. If we now from the equation number one, we also know mg is equal to k delta static. Mg is equal to k delta static. So definitely that will be cancelled out. We are going to have what? This as a final equation. Mx double dot plus kx equal to 0. X double dot plus k by m x is equal to 0. That is our equation number 2. And everybody know what is the equation of simple harmonic motion. X double dot plus omega n square into x equal to 0. If you compare equation number 2 and equation number 3, you are going to get omega n as under root of k by m. K by m. Note down. Now, equation number 3 is basically what fundamental equation for a equation number 3 is a fundamental equation for a linear vibratory system. No, no. Fundamental equation number 3 is a fundamental equation for a linear vibratory system. No, no. Equation number 3 is a fundamental equation for a linear vibratory system. Very, very important. How to solve this equation? How to solve these equations? How to solve this equation? Everybody know how to solve this equation? How many of you believe that there's a CF and PI both will be there? Complementary function and particular integral. How many of you believe that there is a complementary function and PI both will be there? Or only one is there? Very quickly, guys. We don't have time. Very quickly. How to solve this one? X double dot plus omega n square into x equal to 0. Now, everybody know from mathematics, from the differential equation, that d square plus omega n square is equal to 0. How to find the roots of this equation? D is equal to what? Plus minus iota into omega n. Now, my friend, the roots, whenever we have the roots are imaginary, then what is the equation of a motion? What is the solution? X is equal to e to the power alpha t, b sine beta t plus a cos beta t. But alpha is 0. So what we can write? X is equal to b sine omega nt plus a cos omega nt. Yes or no, guys? Please confirm it. These are the very simple thing from mathematics. Very quickly. Now, by different, now it's a very easy task to find out the A and B. They are the constant. That we can find it out from the initial condition, like at time t equal C. Whatever the final equation we will be deriving, already we got equation number 4. But whatever the final equation we are going to get, equation of a motion, that is by putting this boundary condition. But in examination, they can give any different boundary condition. It is not all the time whatever the final equation we are getting that is the same will be valid for all the cases. No, it is depending on different initial conditions. Initial conditions. For example, we have an initial condition at time t equal to 0. We have a x is equal to what x naught, and at time t equal to 0, we are releasing it with the faster velocity. If you put the boundary conditions, you are going to get A and B. Just note down. A and B, x dot, differentiate it. You will be getting this equation. Put the boundary condition in equation number 4 and equation number 5. You can think like this as, I'm not writing this a separate equation, but it is a differentiations. What you can do, you can just, note down very quickly from the equation number 4, we have A cos omega nt plus B sin omega nt. Let us assume, see, you don't need to go through each and every derivation. You don't have that much of time. But my suggestion would be, that will be there in my slide, but you just note down as it is, whatever it is given. Same equation number 4, I am modifying to get the equation number 5. See, equation number 4 and equation number 5, there's no difference. But I'm just converting into some common format. What is the common format? This is the common format. How to get that? No, it's not your task to do that. A is equal to what? X cos phi. B is equal to what? X sin phi. Put that value, you will be getting X is equal to capital X cos omega nt minus phi, where X and phi are constant. X and phi are constant. Now, my friend, whatever the X is there with the time, how it is varying? It is varying cosine. And that cosine function is what? Periodic function. It is doing what? To and fro motion. There is a vibration in the system. You can see this figure. And whatever which is being attached with the cosine, that will be represented with the what? That is said that it is nothing but amplitude of the vibrations. And you can see amplitude will be constant all the time. X, 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 X. You can see that. It will be constant. That means vibration will all the time will be present in the system. Make a note of it. X is the amplitude of the free vibrations. Free vibrations. Phi is a phase angle. You can do sine phi by cos phi. You will be getting B by A. B by A already got it from the previous slide. Now, what is a T? You can write Tn, time period of natural vibrations, 2 pi by omega n. If you differentiate x dot, you will be getting what? This equation number 5. If you differentiate equation number 5, you will be getting x dot. And whatever it is being attached with the sine or trigonometric function, it is always being set maximum value. Now it is a velocity, so it is a maximum velocity, x into omega n. If you further differentiate it, you will be getting the maximum acceleration, x into omega n square. Again, I'm telling you, It is all depending on the different boundary conditions. Done, all of you? All of you have noted down? Note on the example number two, problem number two. Now the spring mass system is there. The spring mass system is there at an inclined positions. Again, there is the moment you attach the mass, there is a static deflection. From the static deflection, we are displacing it by the amount x. If you try to draw the free body diagram, so you can get it like at this free body diagram at mean position. If you draw, you will be getting what, guys? There is a normal reaction force. There is a mg cos theta, mg sin theta, k delta static. So my different no basically mg sin theta will be equal to k delta static. That is the equation number one. Because at the mean equilibrium position, net force has to be zero. Net force has to be zero. Once the motion will be started, then my different, if you try to draw the free body diagram, you will be getting what, mg sin theta in this direction, and the spring force kx plus delta static. Now, in which direction we have disturbed it? We have disturbed in these directions. In these directions. Write down the equation of a motion in this direction. Second Newton's second law. What you are going to get from the Newton's second law? Mg sin theta, that is acting in the downward directions, minus kx minus k delta static equal to what? Mx double dot. From the equation number one, mg sin theta and k delta static, they will be cancelling out. So once again, we are getting the same equation, mx double dot plus kx equal to 0, x double dot plus k by m into x equal to 0. If you compare this equation with the equation number 3, again you can get omega n is equal to what, guys? K by m. So what we are understanding is that a spring mass system, whether it is in the horizontal position like this, whether it is the inclined position like this, whether it is a vertical position in the previous problem, the natural frequency will be k by m. The natural frequency will be k by m. Now we will try to solve the further numericals on the basis of this free vibrations. All of you understanding or not, guys? The concept of static deflections. Yes or no, guys? Hello, hello. All of you understanding? Is it done? Can I move to the next question? Done, guys? No, done. Further concept. Whenever we have a single concentrated load, in case of a bar, shaft, or a beam, in case of a bar, shaft, or a beam, which is having a negligible mass, it is carrying a concentrated mass, just like this. For example, there is a rod, is carrying a mass m. It is a massless, for example. Then my dear friend, in this case, what is the natural frequency of the system? What is the natural frequency of the system? It is a G by delta static. And it is no surprising. We are getting from the same equation. At the equilibrium positions, mg is equal to what? K into delta static. So what is the G by delta static? That we can write K by M. K by M. So what is the natural frequency, guys? We can write K by M or G by delta static. Everybody know natural frequency is what? 2 pi Fn, where Fn is what? Natural frequency. Omega n is nothing but radian per second. Remember, unit is what? A radian per second. If you want to get in hertz, then you need to write what? You need to divide it by 1 upon 2 pi. Please make a note of it. What is the unit in hertz? No, no. Different examples. A rod which is having a length L suspended vertically, mass M is being suspended at the free end. Then static deflection, everybody know that. Mg into L upon AE. If I take example of cantilever beams supporting a concentrated mass, then we can write Mg into Lq divided by 3AI. Hold on. A simply supported beam carrying a concentrated mass. What is the deflection? These are the strength of material equation, guys. If you are not remembering, then I cannot do anything. You have to remember. Please note down the slide. Then all of you have noted down. Okay. Okay. Try to solve this question, guys. Try to solve this particular questions and tell me the answer, guys. So, guys, oh, for this, basically x double dot plus 3x equal to 0. If you compare with the standard equation, then everybody know what is the omega n. It is under root 3. Now, what is the equation? We got it like we got a cos omega n t plus b sine omega n t. And they have given the boundary condition like when time t equal to 0, when time t equal to 0, x is what? 1. Now put that boundary condition 1, a. We got the value of a. What is the second boundary condition? What is the velocity? First differentiate it to get the velocity from the displacement. This is the displacement equation. Differentiate it, my different, what you will be getting? A into omega n sine omega n t plus b into omega n cos omega n t. If you put at time t equal to 0, the velocity will be 0. Put that value. B will be 0. So what is the final equation you are getting? X is equal to 1, x is equal to 1 cos omega nt. They are asking, my dear friend, they are asking when the time t equal to 1 second, what is the value of x? It's a very simple. But what is the omega n? It's a root 3. Now, whatever the value which is being there in the bracket, whatever the value is there in the bracket or assigned with a cosine or trigonometric function, that always must be in degree, not in the radian. So we need to multiply with the what? 180 by pi. If you do that, you will be getting what? B as option. Note down. Now, any one of you try to solve these questions? See, they are asking what is the effectiveness, what is the effective stiffness of the spring mass system. Now, you also know that whenever the springs are connected in series combinations, like this, for example, whenever the spring and mass connected like this, then what is the K equivalent? We write K equivalent as something like this. 1 upon K equivalent will be 1 upon K1 plus 1 upon K2. That is the series combinations. Whenever the springs are connected in parallel, let's suppose two springs are there, which is connected in parallel combinations. Then what is the K equivalent? It is K1 plus K2. If you apply the same concept in this particular problem, then my different what you are going to get? First of all, the spring, let's say this is spring number 1, spring number 2, spring number 3. Spring number 2 and 3, they are connected in series combinations. So I'm going to convert first of all K equivalent 1, and this is the 4 Newton per mm. What is the K equivalent 1? They are connected in series, so 1 upon 2 plus 1 upon 2. So you are going to get K equivalent as 1. K equivalent 1. Further, this 4 and this 1, they are connected in what? Parallel combinations. And if you further try to convert into single spring, which is having a stiffness K equivalent. Then what is the K equivalent value? K equivalent 1 plus 4, which is nothing but 1 plus 4, which is nothing but 5 Newton per mm. Note down. Very, very important. All of you understanding or not, guys? Hello, hello. All of you understanding? Try to solve this particular question. Better you solve this question. Here we can have this question, guys. What is the solution of this question? A figure shows a single degrees of freedom. The system consists of a massless a rigid bar OP hinged at a point O, the mass at the end P. Then natural vibration or natural frequency of the vibration will be what? Now, my different here the mass is there. What I'm doing, I'm disturbing it by the angle theta. If I disturb it by the angle theta, the mass will be coming here. It will be displaced by the amount x, and the spring will be displaced by the amount x of spring. What are all the forces that will be acting in the system? First of all, mg weight will be acting in the downward directions, and this angle is what, my different? This angle is theta. Then what about this angle? This angle will be 90 minus theta. Then what about this component? This will be mg sine theta. And what about this component? This component will be mg cos theta. Further, my different, what are all the further forces will be acting? There is a spring force will be acting in the system. Let me represent it with some different color. I'm representing what? Spring force. Total, how many spring force will be there? Two spring force. The total spring force, if I write, there is a spring force kxx plus delta static. Because the moment you attach the mass, there is a certain amount of static deflection will be there. Now, if we take apply the Newton's second law, the net torque is equal to what? I alpha, which is equal to what? I theta double dot. Now, my different, if you write the net torque is equal to I alpha, now in which direction you are disturbing? You are disturbing in this direction. But in which direction your forces are acting? In which particular direction your forces are acting? Force of spring with a distance called A. In which direction it is acting? Anti-clockwise. So what we can write? Spring force into A minus. What about the mg cos theta? Mg cos theta will be acting in the same direction of a motion. So we are writing plus mg cos theta into what, guys? Into 2A. That is equal to I theta double dot. I theta double dot. Now, my different, it's a very clear now. What is the spring force? Minus k into xx. Minus k into xx. Minus k into what? Delta static. Into A plus mg cos theta into 2A is equal to I theta double dot. Everybody know at the static equilibrium positions, everybody know that the net torque has to be 0. Initially, there is a mg force will be acting in the downward direction, and there was an initial static deflections. mg into 2a, that is equal to k into delta static into a. So my difference, what you can get from here, limit theta tends to 0, sine theta by theta, that is equal to 1 from mathematics. Limit theta tends to 0, what is the cos theta? That is equal to 1. So my difference mg cos theta, that can also be written as mg into a. So finally what we get, minus k into xx into a minus k into delta static into a plus mg into 2a equal to I theta double dot. This and this will be cancelled out from this what guys, from this particular net torque equal to 0. So my difference, what we can get from here, we can get I theta double dot plus k of plus k of what we call x of spring into a equal to 0. Now my difference, what is the xx? Xx can be written as, from this particular triangle, xx can be written as a into theta. A into theta. So further my difference, what you can write, I theta double dot plus k into a square into theta, that is equal to 0. You can further write I theta double dot plus k into a square divided by I into theta equal to 0. If you compare this equation with the standard equation for a equation of a motion for angular vibrating system, then what is the equation of a motion? Theta double dot plus omega n square into theta equal to 0. Just replace x with the theta in the angular vibrating system. So what is the final natural frequency you are going to get? K into a square divided by I. But how to get the I? How to get the mass moment of inertia of the point mass about the point 2, about the rotation point? It's a very simple. K into a square divided by what? M into 2a whole square. If you try to find it out, you are going to get A as option. No, no. Done, guys? All of you have noted down? Hello, hello. Is it done? Is it done, guys? Hello. Is it done? All of you have noted down? Now, further, what we can do, we can start. No, just a moment. Let me add the slide here. Further numerical we will solve, but I want to start the damped vibration also at the same time. Just a moment. Just a moment. What we can do here is that, yeah, just Just a moment, guys. I'm opening the slides here. Hold on, guys. Not on the damped vibrations. Not on the damped vibrations here. Hold on. The fundamental of vibrations. Not on this slide. Very, very important. Fundamental of vibrations. The damped free vibration of a single degrees of freedom. When the damped free vibrations takes place, the amplitude of the vibration gradually becomes small and finally it is completely lost. The rate at which amplitude decay depending on the type of damping and amount of damping in the system. The first type, you have seen that we have the different types of damping. The first type we are discussing is viscous damping. Coulomb damping, we will discuss further. Then we will discuss the molecular damping, that is a hysteresis damping. But as of now, we are discussing only the viscous damping. Let's suppose you have basically you have a system where, let's suppose you have a spring mass system. Let's say you have a damper. Symbolically, we represent this system. Let's say we have a piston rod like this, and we have a cylinder, and this fluid is having certain viscosity called mu. Symbolically, this system will be represented with the what in a vibration chapter like this, and this is called damper. This is called damper. Why? Because now the piston is moving in a fluid. When the piston is moving in a fluid, there is a fluid frictions. Everybody know from the fluid mechanics. Already we have seen. Depending on the velocity profile, we can find it out what is the shear stress, wall shear stress. And what is the wall shear stress according to Newton's second law? Or what is the shear stress? Mu into du by dy. What we can write? Mu is equal to tau is equal to mu into du by dy. From here, you can find the resistive force or viscous force or tau into area, mu into v divided by t into area. We can also write mu into area divided by t into x dot velocity. There we call viscous force. Here we are calling damping force. So this particular damping force for a particular system, mu will be fixed, area will be fixed, t will be fixed. So that we can write what? It is directly proportional to x dot. Because for a given system, mu, area, and T, the gap between the two plates will be fixed. All of you have noted down. Viscous damping means fluid damping, fluid friction. This is the most important type of damping and occurs formally with the velocities in the lubricated sliding surface, dashboard with a small clearances. There it occurs, viscous damping. Is it done, guys? All of you have noted down? Hello, hello, hello. Is it done for all? Hello, 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 hello. Any one of you can hear this? Hello, hello. Okay. No doubt. Whatever the value we are adding C, that is mu into A by T, we are calling viscous damping coefficient or viscous damping constant. Viscous damping constant. So if I want to write for any system, for example, we have a system like this. We have a mass which is connected to the spring, which is also connected to the damper, like this. If I disturb the system, then we can write here, suppose for example, x is there in this direction, x dot is there in this direction. So kx restoring force and the damping force cx dot will be acting like this. If you write down the equation of a motion like this, net force is equal to mx double dot, then what you can write, guys? Minus kx minus cx dot equal to mx double dot. So mx double dot plus cx dot plus kx has to be equal to 0. That is the equation of a motion for a linear vibrating system. But what happened with the angular vibrating system? For an angular vibrating system, my friend, we have this as equation of a motion. Hold on. There, the damping, torsional damping coefficient will be called as C, which is nothing but TD divided by theta dot. What is the damping torque? C into theta dot. I theta double dot plus KT into theta dot, sorry, plus KT into theta plus C into theta dot equal to 0. That is for angular vibrating system. Note on the differential equation for a damped free translational vibrations. Just note on the figure. Then we will close the sessions. We will be starting from here only in the next class. Just complete it. All the slides. There is a mass, spring, and the damper. Just draw the free body diagram and note down the equation of a motion. And how to find the solution of this equation of motion, we will see in the next class, right? All of you understanding or not, guys? All of you have noted down? Hello, hello, hello. Is it done? Is it done? Okay. So thank you all. We will be covering more numerical regarding the free damped vibration, free undamped vibration in the next class, right? Thank you all. We can leave for the day.